Hi, my name is Claudio Barbura, and I'm a director of engineering at Blueprint Technologies. And welcome to my presentation on video analytics at scale. Right, all these acronyms: deep learning, computer vision, machine learning on the Databricks platform. So let's get right into it. The agenda for today: I'll just start with a live demo of our video analytics solution because to me that's the best way to provide a context for the rest of the presentation. Then we'll dive into the solution architecture, and then I'll go over the lessons learned throughout the entire solution building, everything from infrastructure to the deep learning aspects, to the machine learning aspect, the data science, all the engineering data science efforts to be put into this, to build any solution. And we'll leave some room for Q&A at the end. So here's our video analytics solution that we built in a very short amount of time. It was almost 3 months of very intense work. The purpose of the solution was to build a very narrow use case into video analytics, and it's about now monitoring video traffic from traffic cameras. And the goal was to showcase our expertise, our capabilities, and the intent is to provide as a free trial in the Azure Marketplace. And one of the prerequisites was to use Azure cloud services for this, right? So the entire solution is built using open source tech, but it had to be deployed in Azure, which we did, and I'll do a quick demo of it. So the solution will allow you to, and I'll show you what it needs. So basically the solution, after you deploy from the Azure Marketplace, it needs a storage account where it's going to pick up the videos from and it's going to output some data. It needs a Databricks cluster to do all the processing, can be CPU or GPU. And then in order to have Azure Active Directory single sign-on, you just have to provide the app registration, right? So Databricks configured. I'll share what that means. Once you configure and then attach these assets to the application, now the solution deploys on one VM. It's a Linux VM in the cloud, and then you attach these dependencies. It's important for us to know what kind of cluster, ADB cluster, you'll provide for all the data processing, because that will determine which image to load into the Databricks cluster, which Docker image to load, because it will have all the dependencies required for us to process all the OpenCV, all the object detection and tracking libraries and so on. So once you go to Workspace, you can create a new workspace, and I'll do that right now. We'll provide it a name, AI Summit Demo, and then you go in and you connect your blob storage account, and then you pick a video that you want to process. I'll pick a short video just to start it off. Intersection 4, you get a preview of it. You can see now this is a animated video that we created, and you see this individual here in the middle of the screen doing a donut, and that's going to be relevant for the demo moving forward. But once I'm happy with my video selection, I'll say, fine, let me just go ahead and process it. I could look at the advanced settings and change the defaults, but basically the application will extract traffic patterns. We'll find peaks and valleys, if you see in the picture, surges and dives and oscillations in traffic patterns. We'll also find anomalies, and then you can configure the anomalies, and then you have some configuration for the processing of the videos. So some of the parameters here are important for smoothing that we'll see in the video, and I'll talk about that in detail in the slides. How to smooth out these curves, because there's a lot of noise coming from an imperfect object detection process. It's never perfect. There's errors, so we have to do all this extra processing at the end. And once I'm happy with my default settings, I'm going to go ahead and say no around the analysis. So what happens here is this video is now being sent to the Databricks cluster for processing, and then any events, any signals coming from the processing are being sent back to the analyst. So They'll have the progress bar here. They'll have the monitoring pipeline. They'll be able to see what exactly happens with my processing. What happens behind the scene is object detection. It already kicked off. Then I will be tracking. Then video stitching with the bounded boxes, and then the insights extraction at the end, behaviors and anomalies, and then building similarities between videos. Right. So all of it is done obviously in parallel in the cluster. So the progress of this process is being sent to the analyst, right? So they don't have to. They can start analyzing the output immediately. It takes a while to just warm up the processing, but in the meantime, I will switch to an existing pipeline because it was already run before to show what kind of insights you can find from the application. I'll pick one of the videos, this one. So you'll see object detection, bounding boxes around the object that are found in traffic. For that, we're building an object detection graph. So you can move my camera from here. You can see that the detection graph is in sync with the actual video. So you can scroll to and zoom into to a particular moment in time in the video. This is not obviously processing videos from blob storage, so it's not yet connected. Now this solution is not yet connected to live traffic cameras because that's something we will do in as a professional service exercise for when we build custom solution for customers. But for this free trial in Marketplace, just to showcase our tech, you connect to blob storage, the existing videos, and then we do the analysis. So you see the zoomed in area. The patterns that we found in this video, everything from oscillation, peaks, values, and surges, you can zoom into them, and you can see that there's a peak which consists of two events: a surge event followed by a dive event, and that's showcased here in it's highlighted in the object graph, right? So if you can look at that particular behavior of interest, you can spot it on the graph. Also, besides detecting these patterns, we also do anomaly detection, right? So, and that comes in this canvas here, and we're looking at what are the most common paths, all the paths in the vehicle trajectories in the video, and then we're finding the average paths, and obviously at the end the anomalies, right? What are the most rare paths in the video? And in order to showcase this better, I'll switch to. Before I do that, I'll show you what also the app provides. Now it provides you with the configuration settings. So this is where you can come in and change maybe the rate of change for the value, right? I want vehicles per second. I want steeper curves. Now that would be basically extracted here because I care only about sudden changes in traffic behaviors. So you can configure all these parameters and rerun the analysis. Now, basically, after you configure that rate of change, you can make it. Now, I want steeper curves for the decreases of for the valleys. An increase followed by a decrease of vehicle count followed by increase of vehicle count. You can change that rate and just say reanalyze, or basically that's happening after the processing that happens in the cluster and doesn't use the cluster anymore, right? But what's happening in the Spark cluster? And we have already this existing video that's been processed. And you say you have a bunch of segments, video segments, and then we have batches of segments. So the reason we do this is because once we send a video in the cluster, we fragment it into multiple parts, and they're being processed in parallel. So they're not all tasks are equal, not all video segments are equal because of the richness of the information in those videos. So they're being processed at different times, or maybe the cluster, some nodes in the cluster are slower than the others. Anyways, the solution and the service, the Nash service acts as an aggregator, and it's waiting for all these segments to be processed. And at some point in time, when it has enough segments to process, in a list of consecutive video parts, it's going to trigger the rest of the analysis, like behavior extraction, the anomalies, and then building the similarities between videos. After tracking and video stitching, obviously. So everything is being monitored and shown here because it helps now the ops team figure out if there's something wrong with the cluster or maybe something wrong with the VM. And as you see in the slides, because of the lack of time, we could not push everything to the cluster, and that was one of the issues when we're running multiple videos in parallel. We're now running in a VM, which is not a control environment, doesn't have a resource manager, right? So we would rather push all this processing into the cluster where we have a resource manager, we can control the throughput. So, and in the end, now it gives you the total duration, and there's at the end of it, when everything, the video is being stitched together and tracking is being stitched, we're running that post-processing yet again, so we can find the final anomalies. But the reason is we do this partial processing because we want to give the analyst the ability to analyze videos before it all ends, right? So mid videos, they can still look at the all those detection graph, the behavior, the extract behaviors, or the anomalies without waiting until the end, right? So something about the before we go back to the slides about the cluster. So we can run on both GPUs and CPU clusters. There's more work happening right now for optimizing against GPU cluster. I mean, we're moving to SPARC 3.0, so we can have GPU aware scheduling. But this particular deployment is connected to this 10+1 clusters. There's like these type of instances. And if you notice, what's key here, this Docker image, right? This is from us now, Blueprint, from our Blueprint container registries. And it has an image that will include all the dependencies required to do object detection, the computer vision processing, and the tracking in the cluster, right? The solution is available in the Azure Marketplace for free, so go ahead and give it a try. Point to your videos in blob storage, and off you go. All the data all the insights are extracted and dropped into an Elasticsearch, and this is a Power BI canvas that shows connecting directly to that data, and you see that my particular intersection, the low traffic 3 was my video. That's the actual raw data behind it, right? So it's imperfect, and you'll see how the object graph detection involves smoothing algorithm to remove all this noise, right? So I'll talk about that in the slide. So this is the architecture of the solution. As I mentioned at the top, the requirement was to push it into the Azure Marketplace. Once you download it from there in your own subscription, you get basically the one Linux VM in Azure. Now, solution obviously includes deployment scripts, all based on Ansible and Docker Compose. Then we have the Azure Active Directory component there. Now, as you remember, you have to register the app, and that's a manual process behind the scenes. You register the app with Azure Active Directory, then you come back and configure it to use that for authentication. Then what's in the Linux VM, and that's this big box in the middle here. Well, we have the management console, which you've seen is done basically all the rendering, all the analysis, the video rendering, the provisioning, the configuration, everything happens in that web console for the analyst and for the administrator of the solution. Then we have two services, JNash and PyNash. The JVM service, which has all the APIs, the video manager, the pipeline monitor, it does the encoding, and basically the WebSocket push, basically sending all those insights down to the web application, so we can inform the analyst that there's more segment, there's more behavior, and so on, right? So that's the JVM, and then the Python service does now all the heavy lifting. Now it's actually it's the PySpark driver, and it does all the object tracking correction, the feature space generation for the behaviors anomalies, event aggregation, and similarity, right? I didn't show the similarity. Basically, you click on that similarity canvas, and you can find similar videos to the one that is being processed, because that was the whole point of the analyst. Doesn't have the time to watch multiple videos at the same time. So the solution will build a similarity score. And the similarity is based on the behaviors detected in the videos, not on the actual environment. That will be something for our roadmap, to look at the similar environment, similar footprint, and build a similarity score on that. So that's the Python service, and then everything is being stored into Elasticsearch. So that's part of the VM. And these are the external dependencies. The Azure Databricks cluster that does the actual heavy lifting, the detection, the object detection, and the classification. Also overlaying the bounding boxes over the video segments, and it's doing the object tracking on those segments, right? And then blob storage, obviously, for where we pick up the videos from, and then the some output from the processing is also stored there. What's not in Elastic, it's in blob storage, right? So that's what now the Spark just work with. So lessons learned on the infrastructure side of things. I'll quickly go over that. What's the solution? One Linux VM plus the dependencies. What's key for us to shift all compute from the VM to the Databricks cluster, because we have a control environment, a resource manager. So then we can avoid having contention, especially when you're running multiple videos in parallel. The most expensive part is the video generation, the FFmpeg part, and that with multiple videos can cause the VM to basically freeze. So we're in the process right now of moving all that video generation, the placeholder generation into the cluster. We're pushing our own Docker images now with OpenCV, PyTorch, scikit-learn, everything to the Databricks cluster. We're using now Databricks container services that has to be enabled for the cluster so we can push those images. Some optimization that we learned during, as we build this and we release newer version, for the CPU architecture, having a PyTorch bound to one thread basically give us 2 to 5x in performance. That was huge. I guess the lesson learned here is that let Spark and it's do the work basically. If you have tasks running over segments, let them just run with one thread at a time. Otherwise, but basically, what was happening before, each task in a VM in the cluster would create a bunch of contention now with the other ones. So binding it to one helped a lot. On the GPU architecture side of things, we had to move from mxnet to pytorch, and then because it just wasn't working. mxnet wasn't working for us on GPU side of things. And then these configuration options for running basically the tensor on the CUDA device that give us some lift. The biggest lift we had from basically all these tasks are loading the model for object detection, and they were loading it from this. So that was a lot of time wasted with that. So as soon as we introduced that model as a Spark broadcast variable, there would be cache basically and then shared across tasks. We had this 2 to 4x performance improvement. On the GPU now, because the GPU memory is because scheduling was done before on CPU, right? You have how many CPU cores, and then all the task schedule was done based on that. That would create too many tasks running parallel on one node, and that would basically cause the GPU out of memory conditions. So now with Spark 3.0, we're in the process of moving to GPU-aware scheduling, where we can know how many actually GPU processes we have, and then bound that, basically do the partitioning based on that number instead of the CPU cores, right? So now that's how we can avoid out of memory when you're running, especially running multiple videos in parallel. And I'll show you the performance between the two, the GPU and the CPU cluster at price parity. Pretty much the GPU is faster and it's cheaper to run on GPUs. The one lesson learned is now, well, the type of instances, GPU instances we had in Azure are this Tesla V100, which are just too expensive. They give us 6 cores and 112 gigabytes of RAM, we call it CPU RAM, but really not useful to us. We would rather use something like Tesla T4s basically less cheaper GPUs, which is no less RAM and less cores because we don't use them, right? For our particular workloads, for object detection, we don't use that much. So we would have even better numbers if we had different GPU instances, right? So in the future, we'll optimize towards that type of instance. This is the graph for GPU versus CPU for a few videos that we ran. You see it's just that much faster on GPUs, and it's if you do a price comparison, it's just cheaper to build on GPUs. And this is the data behind those graphs. Lessons learned in object detection and tracking. So we moved from initially we used one set of model that's a faster RCNN, ResNet, basically the ResNet class of detectors, and their performance is measured in mean average precision. It's 37, and the 21 frames per second. That's the speed of the model. We moved to a faster, more accurate, efficient DET architecture, and that has like from D0 to D7 different models, and they have obviously different costs. The higher the number, the higher the precision, but also the higher the cost, right? So the slower it is to process. So that has a mean average precision of 46 now, and slightly faster, 22.7 frames per second. That efficient DET D3, which we pick by default, trained in that Microsoft Cocoa data set. And the classes used are bus current tracker because that's what the narrow use case in the application is doing. With the detection confidence threshold at 40%, all this is configuration based. So we learned is not all videos are equal, algorithms are not perfect. What's key to us is to expose these configuration options in the application, ideally even in the UI, so we can easily, quickly fine tune it if a new video shows up, right? And mentioned earlier, we had to move from mxnet to pytorch due to the GPU architecture requirements. What also helped is batch framing. Now, initially we didn't do that, and as soon as we started batching, basically take a batch of 5 or 10 frames, load it into the GPU, do the object detection before you switch context and do the tracking, because the object tracking is done on the CPU. So this context switching between GPU and CPU can be expensive, and batching solved a lot of that problem. For the tracking, we started with our own strategy, but then we moved to Fairmont, and it works. Like I say here, it's a default tracker right now. It's 10 times faster when it works, right? There's some videos where it doesn't do a good job, and in that case, we fall back to our own custom tracker, and that's using GDE, joint detection embedding, column filter, and template match. So it's a combination of techniques that will, in those cases, give us better tracking, but it's much more expensive to run. So there's a trade-off there, but we can configure that. And this is the object detection model. You see the curve for the efficient DET architecture. Now you have the score on the left, on the y-axis, the median average precision. The higher the D, the faster, the slower, but the higher precision, right? So that's what we settled for D3 here. It's a good compromise, a good average precision, and for the good cost. And on the horizontal axis, you have the flop. Basically, that's the cost. Now, how many floating point operations it needs to build that. And the ResNet family of detectors are here, so less precise and slower, right? So that's how we change that in the architecture. Lesson learned with the behaviors and the behavioral patterns and the anomalies. The anomaly for that intersection 4 video is the donut performed by that driver. So that's detected as an anomaly because it's obviously not something you would want to see in traffic. So we're basically we're using clustering here, and the cluster representatives are pseudocentroids in non-uniform vector length feature space. I know that's a lot of words there, but basically what we're doing is we're building all the vehicle trajectories, and we're clustering them, and we're using dbScan for short video and agglomerative clustering for long videos. Those are the clustering approaches that work better for the independent on video length. And Rarity is computed as distance from the cluster centroid, right? So that's how we determine what are the outliers here and what are the rare vehicle paths, and that's how the donuts showed up as an anomaly. And so I showed in the Power BI canvas the actual raw data, and that's the raw data at 30 frames per second. So a 30th of a second, right? That's the frequency, and that's how the data looks like. And after we're applying our timescale-based smoothing algorithms, and that parameter is a key. Like, do I want to see oscillations now smoothed at 1 second or 7 seconds? If I'm looking at a 4-hour video, I don't want to see behaviors that are at that granularity at no second. Maybe I want to see it at minutes. I want to see patterns at minute interval or 5 minutes intervals. But if it's a short video, 30 seconds video, I want to see it at a more, at a lower rate. So that parameter influences the smoothing of the curve, right? If at 1 second you see the orange curve, at 7 seconds, you see how it's actually attenuated at the higher rate. And we're using low pass filters and Fourier decompositions for eliminating basically the noise from these from the raw data, from the raw curves. And that's how we build that object detection graph, and that's how it's so smooth. And that was it. Now, please provide some feedback, and we have time to take some questions from the audience. Thank you so much for attending my presentation.